Thank you very much. It's a great pleasure being here. I would like to thank the organizers for a very informative meeting on all kinds of topics. I'm really enjoying it. So the talk I'm going to give relates to optimal mass transport and some of the material that you heard a little bit earlier. It focuses on what's called Schrodinger Bridges. So I'm going to give a little bit of an overview at the beginning. I'm going to touch, maybe some of you know some of the material on optimal mass transport I'm going to bring in, but I would like to give the context. So the subject is basically interpolating probability distributions. This interpolating and fitting models to data is what we do in engineering. For a long time we've been trying, and many in the audience of course, how to smoothly interpolate, for example, images, or this is power spectra. These are different examples that sort of simulate situations where you have marginals and certain assumptions, and you try to interpolate or try to find out the flows. So the whole idea, the whole context is you have data which represent one-time marginals, typically at 2 points or now at many points, and you would like to determine a reasonable model for the flow that passes through these points. Optimal mass transport provides the tools for this. Schrodinger Bridges, if you haven't heard of this, is basically a regularized version of the optimal mass transport, which goes back to Erwin Schrodinger and relates to stochastic control as well. So again, the outline, I'm going to give a little bit of a context on optimal mass transport and Schrodinger Bridges. Then I will discuss some earlier work by our group on splines in the Wasserstein space, and the subject of today's talk, which is multi-marginal Schrodinger Bridges, and show that distribution splines are zero noise limit of those. So basically, in a nutshell, if you'd like to see what this talk is about, it's Schrodinger Bridges, multi-marginal, that are zero noise limit, that measure value splines are zero noise limit of those. So let me again, for some of you that have not had the background in optimal mass transport, give you a couple of slides to present the context and some of the terminology. So the problem of optimal mass transport goes back to Gaspard Monge. The history maybe you know, he was one of the founders of the École Polytechnique, and he came up with this natural question of trying to see what is the cheapest way of moving mass from one point to another. The story is about leveling Earth so that you bringing some cannons over, etc. So basically, you have a mass here, and you'd like to fill in some holes. So how do you move it? And the cost was to infimize some integral of the mass that we move from point X to point T of X. So T is the transport plan of some cost. So initially, this was the one norm, but the two has great advantages and relates very much to more recent developments of the mass transport. I'll spare you the details, but it's a very beautiful, a lot of connections. And that is what we call the Wasserstein 2 metric. This is the square of that, when you take 2 over there. And basically, the push forward of mu is one of the distributions, is the nu is the other, and that's the requirement. Now, this is a very difficult problem to solve, nonlinear in T, and it took many years before people came to grasp this. Long treatises by Abel and others, and basically the problem stems from the fact that if you have here, for example, 1 Dirac measure, and you like to split it into 2 Dirac measures, you don't have a transportation plan, so transportation doesn't exist. So then, of course, the next phase of this whole story comes with Leonid Kantorovich, who regularized it, and he said, well, let's look at couplings let's look at joint distributions between two sort of random variables that have the densities that were given as corresponding marginals. From now on, I'm not going to talk about measures. They will all be absolutely continuous. So there's going to be a probability density. Okay? So mu and nu are measures, and from now on we have rhos as marginals. So this is one marginal and this is the other. In the previous picture, you can think of this as one marginal and the reflected side of reflected this one as another marginal. This is a one-dimensional problem. So in the Kantorovich setting, he looked for transporting from x to y, and this is the transportation cost. So you visualize those as living in two different spaces, and you visualize the joint distribution as being in the product space. So the constraint of the previous slide becomes now linear, and this becomes simply a linear program. So he understood this and developed linear programming and duality theory to solve this problem. And of course, now it becomes almost trivial. When the distributions are nice and smooth, there is a transport map. So the joint distribution lives on, this is the graph where the joint distribution lives. So you think of it as distributed Dirac deltas. And this is actually the transportation plan. So when, if this was one Dirac and these were two Diracs, you would see here two dots. So there wouldn't be a map. But when there is a map, this is called a Monge map. Okay, that maps one distribution to another. So if everything is smooth and nice, you can construct a Monge map. Now, the next chapter started being written in the 90s and more recently, especially Benhamou and Brenier, Macan, Gangbo, Otto, Villani, and many others, where the people realized that you can look at the Wasserstein metric in a different way, and we heard about the Wasserstein manifold before. You have basically an almost Riemannian structure in the space of distributions, and the flow from the beginning to the end can be affected. You don't look at the transportation plan, but you look at how the masses flow from the beginning to the end. It turns out, because the underlying space is a geodesic space, if you think of particles, they follow geodesics. In fact, the flow obeys this continuity equation and minimizes this action integral, which is basically, you see here, kinetic energy, rho times the square of the velocity. In the previous lecture, the square of the velocity was shown as a gradient of some potential. And the reason for that is because the optimal flow should be curl-free. You don't have rotation. So this is really an action integral. You integrate over space and time. 0 to 1 is time. You move from beginning to end in one unit of time. Rn is space. And this is the Wasserstein. And you can think of it as expected value of, and you can give a stochastic control interpretation of that, because you can think of V, for example, as a control action. So you can think of the optimal transport problem, right, of matching the two marginals as the flow between them. The marginals may be given, you're looking for example, for the V. The V could be thought of as a control action that steers one to the other. There are many problems you can put in this context. Now, let me shift a little bit, and I'll talk to you about Schrodinger bridges. Schrodinger bridges, again, is a stochastic version of optimal mass transport. The problem started with Erwin Schrodinger in 1931, and he wanted to understand his own equation, famous equation, in classical ways. So the story is quite long, and it took many years before this is understood properly. Stochastic mechanics came out of it. So there is a lot of more details I'm not going to cover here. So he conceived of the following basic problem. He said, suppose I give you, in this simplest setting, a cloud of Brownian particles. These are the two marginals that we have, rho 0 and rho 1, at instance t0 and t1. And you think of these as Brownian particles. So, for example, you have a box over here with, let's say, oxygen molecules, and I open it, and they're all here. 5 minutes later, I find them over here. Now, my prior is that they're Brownian, and they should be diffusing everywhere. But you cannot tell me they're not here because I measured them. So that is the starting point of Schrodinger. So you're given the two marginals, and they're not compatible with the transition mechanism. So something unlikely happened. So the particles move from here to there. And he asked the question, he said, given that, I want sort of some conditioning. I would like to find a new probability law on the path space that is consistent with the two marginals. And this is the question he asked. Of the many unlikely ways that this could have happened, which one is the most likely? So again, it took many years, almost 50 years, before this was understood in the context of large deviations. And basically, the question rephrased in modern language is the following. That's what Schrodinger effectively asked. And by the way, he answered the question. It was really remarkable. The story is very, very interesting. So, but let me phrase it in modern language. W is the Wiener measure on paths. So think of particles that live over here, and they have this distribution. And if you let them alone, then they will just diffuse all over the place. But now you specify the other marginal, and this is this one. And you would like to find the most likely path. So the Schrodinger bridge problem amounts to minimizing the KL divergence, or I use H later on for this, relative entropy, between the two measures, Q and W, which is expected value with respect to Q log dQ dW is the Radon-Nikodym derivative of one to the other. And this is very, very important to realize here that W and Q are measures on the path space. In other words, this is a much bigger space, right? This is C01 functions here. So it turns out, and this is basically Giovanni's theory, that the relative entropy between those two is the minimum between over densities and velocity fields of an action integral subject to the Fokker-Planck equation and the given marginals. To understand this in this context, it took a very long time. It started being realized in this way in the 80s and 90s, basically. Now you see here the similarity to optimal mass transport. You have again this action integral, and the difference is the Laplacian here. Now there's another very interesting twist to this, that you can rewrite the Schrodinger bridges. I go back to the previous slide. You can basically have the same optimization problem, and you can get rid of this expression here, the Laplacian. You can bring it in. You can make it disappear by changing the functional here. And so you have the continuity equation, the marginals, and penalize the transport with a Fisher information cost here. Those two have interpretations in the context of stochastic mechanics. This is also kinetic energy. This is kinetic because it's mass times velocity square, and this can be given the interpretation of some osmotic velocity. So this whole thing is again some sort of a kinetic energy. And this is a reversible formulation of that, which is interesting in its own right. Now, let me say this is one slide about what is lurking in the background, interest in the Schrodinger bridges, which is again a relaxation of the mass transport. So optimal mass transport you penalize the cost subject to the continuity equation. In Schrodinger bridges, you have a diffusion. Now you can think of diffusion with a varying coefficient here, diffusivity coefficient, and as epsilon goes to 0, you can show, and there's a lot of work on that, Christian Leonard and others, and of course it relates to Marco Couturi's fast solution of an optimum mass transport. You can think of solving Schrodinger bridges for different epsilons, and as epsilon goes to 0, you recover optimal mass transport. So this is a very, very simple example. You have two marginals. One, you have a peak here, the other have a peak there, and you try to transport from one to the other. And I don't need to preach to the converted here that optimal mass transport is nice, because you don't get this fade in, fade out effect. Like if I try to linearly interpolate, the blue will go down and the red will go up, right? This is called fade in, fade out, which is a no-no in image processing and other things. So optimal mass transport, and that's the reason we're interested in this, it smoothly moves things about because it's weakly continuous transport. So anyway, here you see, for example, the Schrodinger bridge between these two marginals where you have a high diffusivity, so you see a little bit of what's called lazy gas. I mean, the distribution spreads out before it brings back up again. And when the diffusivity goes to 0, you see, here it goes from very large epsilon to small. It's basically the same thing as optimal mass transport. So that's a reason why one would be interested in that. So now let me shift gears a little bit and talk to you about interpolating many points. So when we interpolate many points in Euclidean space, of course we can use piecewise linear interpolation or other interpolation if we assume error, and we can come back to that. But a very natural way, which goes back, of course, many years, is to use splines. Splines means you smoothly look for curves that cubic polynomial, for example, of higher order polynomials that fit those points. And Halliday, I go until what, 11:30?
Oh, well, maybe a bit shorter than that.
Oh, okay, because I thought it was half for each.
Yeah.
Okay, I'll go faster. So Halliday's theorem is that splines are minimizers of the second derivative, meeting all these points, and admits a unique solution which cubic interpolation spline. The natural splines don't have any constraint at the ends. So the problem here is to interpolate in Wasserstein Spain probability measures rho i's. The reason for that is we're interested in animating images, signal processing, and so forth. And some early work a couple of years ago was by our group, and also Benamou, Gauyeg, and Vialar. And so the idea here is because you try to match. So you don't want rough corners, so you'd like to penalize acceleration, and the natural formulation is this. So you have some probability law on path spaces, you penalize acceleration, and this has to be consistent with the margins you are given. All of this simplifies when things are Gaussian and becomes very, very easy, but even in the general case, it's quite natural, and I'll talk about algorithms and so forth. So this is an example where we have, for example, here 4 Gaussians, and would like to move from this to this to this to that. So if you were to do a optimal mass transport, for example, you would go from here to there with displacement interpolation, then a straight line here, and then a straight line there. Now, what we want is we would like to penalize second acceleration. So naturally, the particles that leave from here are going to visit this position, but then the cost in the acceleration around here is important, so they will smoothly go around, and this is distribution natural splines. So the problem of transporting is, while minimizing squared acceleration, and it generalizes to more general other dynamics, for example, the transport plan amounts to how much mass flows along C2 curves with square integrable second derivative. So the distributional spline problem is to find exactly this minimizing. So the probability law right? So the push forward when you stop it at the TIs has to be rho i's. Now, many nice things have been shown already. For example, there exists an optimal solution to this problem. The following things are equivalent. If P is an optimal solution, then the probability law on path spaces, okay? So the particles can go from beginning to end any which way they want, right? They can go in a very linear way, anything else. But the probability law is only concentrated on spline curves, on piecewise cubic polynomials. So the probability is 1 there. And then if you slice it and you have the marginals, so you just stop it at those points, this is a solution to a multi-marginal problem, and that's one way of solving things. So you minimize now over a joint on a product space of n spaces here, where there is a cost. And the cost is the cost of transporting a single particle between positions x0, x1 up to xn. Now, a closed form expression for this doesn't exist, but you know, if you have 3 points, you can do something, and in general, you can write it as a minimizer of something which is easy to handle. Now, uniqueness for this has not been established. Now, a nice alternative formulation is to expand a little bit the underlying space and look at the phase space and seeking Monge solutions. So you have a cost on a space of positions and velocities. You minimize again the acceleration, and you interpolate data like this where the VIs are free. So again, you can formulate it like that, with marginals being this, and is equivalent to that. And you can prove that any sufficiently regular solution is concentrated on a graph. So it's like you have Monge-like solutions, but you have to lift it to the products of positions and velocities. Monge-like meaning that you have a map, actually, that moves in from the beginning distribution to everything else. Now, there is a distributional formulation of that we can write it a little bit more like in Benham-Bernier also setting, where you have minimizing over. Now, this is a distribution on velocity position space, right? So when you integrate against V, it has to be the rho i's at the position TIs, and you have the continuity equation here, which has acceleration as well. So A here is acceleration. Now we move on to the multi-marginal bridge problem, where you have the Brownian particles accelerating and the position here. And the problem is, we pose it exactly like in the Schrodinger setting. You minimize the posterior law P on path space that minimizes with respect to the Brownian prior. Brownian is the law that is imposed on this system, on the path space of this by the Brownian excitation. And you try to minimize the relative entropy. Once again, following Gessanov, the relative entropy becomes a quadratic expression where penalize the square of the acceleration. And the problem multi-marginal Schrodinger bridges is very much the same as the splines, except you have this Laplacian, which is with respect to the V parameter only. You can prove a number of things, existence and uniqueness for sure. And now we're interested in the limit. Everything follows verbatim, almost. You know, the limit when epsilon goes to 0. Here I have a square root of epsilon just to, okay. And then you can, as epsilon goes to 0, this Schrodinger bridge problem slowed down approximates the distributional splines, as you would expect. There is a time symmetric formulation. You can get rid of the Laplacian over there at the expense of putting a osmotic velocity acceleration there. The catch here is that because you have many, that you are doing you're on a bigger space, you cannot decouple it completely. Contrary to the usual case, the marginal, this no longer depends on the marginals at the two ends. So you have to, so it depends on the initial distribution of velocities, which is something open in this setting. Okay, and here we're going to running a little bit late, so I just want to say algorithmic aspects, very similar to Schrodinger bridges. You try to minimize the relative entropy with respect to some free energy expression like, and the cost of transporting is a summation of costs. This is when you have position and velocity. It's the summation over segments. Of course, the velocity is free. And a natural way of solving this is by iterative Bregman projections. The constraints are convex. This is convex. So you can show that the solution is basically scaling of this exponential cost. And these are simply Lagrange multipliers. And you can compute them iteratively by projecting, minimizing the entropy with respect to each. This is a synchron type of iteration. Okay? Each projection is onto one of the factors, and you can write explicitly the expressions. So you start from a distribution, and you keep correcting. So just to conclude, this is a natural extension of the Schrodinger bridge problem to many marginals. So the interesting thing is that you have positional information. So you have not complete information. And then you can extend this to more general dynamics. And the algorithm is relatively efficient, though it looks complicated, of course, on paper. So with that, I would like to thank you for your attention.
Very nice talk. Do we have questions?
Well, I must have been very clear.
Maybe I can ask you. No, it was a very nice presentation. So you were talking about it in terms of priors. So I mean, as if I make some observation, I have some evidence that would be those margins, and then I would have a posterior probability. And the other way is to think about, these are kind of givens, and I want to get an optimal transportation in between.
Right.
So this is an analogy that, so to what extent would one be thinking about this as a constraint optimization versus a posterior probability on some belief?
Yes, yeah. I mean, it can be seen in different ways.
Yeah.
You see, this goes back to how synchron came up in statistics, right? That you have marginals, which you really believe because you have more data.
Right.
And then you have few measurements on the joint.
Right.
The joint is like a prior, right? That you have data, but you are not fully sure. The margins are something more safe for you. So then you'd like to correct the prior, and then you minimize the relative entropy. And again, this is the rationale of how synchron iteration started coming about in statistics. They started taking the prior and then adjusting with scalings, repeated corrections. So you can view it in different ways. This is more like okay, great. So then, thanks again. Thank you very much.